In question 11, two blocks are connected by a string that passes over two pulleys. Block 1 is hanging from the left side, while block 2 is hanging from the right side. The question tells us that the masses of the string and pulleys, as well as friction, are negligible, because the mass of block 2 is greater than the mass of block 1. If you think about it, block 2 would descend and block 1 would ascend. Block 2 has a greater weight, and both blocks would have the same acceleration a, since they are connected by the same string. In part A, we need to draw free body diagrams that represent the forces exerted on each block. The forces present on this pulley system are only weight, which is mg, and tension. The weight vectors always point downwards because of gravity, and the tension vectors point upwards because they support the blocks vertically and counter the effect of weight. Since block 2 has a greater mass, and thus a greater weight than block 1, it would have a greater magnitude for the weight vector. The tension vectors for both blocks are the same, since they are connected by the same string, and their magnitudes are equal to the difference between the weight of the second block and the weight of the first block, which is also the net force. In part B, we need to find the value of A in block 2 in regards to M1, M2, and G. In this system, the value of A acceleration is the same for both blocks because they're connected by the same string. Using the free body diagram, we can write two equations that describe the forces acting on these two blocks. In block 1, the equation is m1a equals T minus m1g. The tension is pulling this block up against the force of weight. In block 2, the equation is m2a equals m2g minus T. The weight of this block is being pulled down. The weight is pulling down this block against the force of tension. Combining these equations so that we can eliminate the variable t and isolate the variable a, we get m1a plus m2a equals m2g minus m1g. Factor out the a from the left side and factor out the g from the right side, and you get m1 plus m2 times a equals m2 minus m1 times g. And to find a, you need to isolate the variable a on the left side. So divide m1 plus m2 from the left side, divide m1 plus m2 on both sides of the equation, and the end result you get, which is the answer, is m2 minus m1 times g divided by m1 plus m2. In part C, a third block is added to the system with a mass of m3. It sits on the table. We can use the equation we derived in part 2 to find the acceleration of the blocks in the new system. Because block 3 isn't hanging, its weight can be negligible for the numerator, which is the net force. When we add its mass to the denominator of the equation, which is the total mass, the value of A becomes smaller than it was originally. Also, since the net force of the system is the same, we can look at the equation F equals ma to find the acceleration, to find that the mass and acceleration are inversely related. So, in conclusion, the magnitude would be smaller. The magnitude of acceleration would be smaller in this new system because the total mass of the system becomes larger.